Hello everyone. Today we'll be covering part 2 of chemical bonding, where we'll be covering like the VSEPR theory, which includes lone pairs and bond pairs, and we'll transition this into the molecule shapes and bonds. We'll also be talking about electronegativity, bond polarity, and how it gives rise to intermolecular forces. Elaborate on the types of intermolecular forces that is within your syllabus and compare their strengths, and give a trend or identify a trend of electronegativity. And lastly, the change in state, like what bonds are broken and what bonds are formed and whatnot. And additionally, I'll also be talking about something that's a part of the Group 17 lesson, which is the trend in melting and boiling points down Group 17. Anyway, so let's talk about firstly the VSEPR theory. And this is what is based off, like this is what the molecule shapes and bonds are based off of. And the VSEPR theory, or better not, like the full form is valence shell electron repulsion. Sorry, not electron repulsion, electron pair repulsion. VSEPR theory. This is what the full form is. And recall again that electrons, like the lone pairs, they're negatively charged, so there's like a repulsion amongst them, and even amongst the other lone pairs there's a repulsion. So for instance, this lone pair, because it's negatively charged, will also repel these two lone pairs, and vice versa, right? So that's what the VSEPR theory is. And the additional point of the VSEPR theory is it like describes the strengths of repulsion. So a lone pair to, okay, let's just wait. Let's just say lone pair is LP, and bond pair is BP. Normally BP is boiling point, but for now let's just say BP is bond pair. Okay, so the repulsion between an LP and LP, lone pair, is greater than repulsion between lone pair and bond pair is greater than the strength of repulsion between bond pair and bond pair. Sorry, bond pair. Okay. So what this basically states is that when there's a lone pair present, like the interactions between lone pairs, will give a stronger repulsion than will give a stronger force of repulsion than interaction between a lone pair and bond pair. So for instance, let's say this is lone pair, yeah, and there's a bond pair and a lone pair here. Okay, so this lone pair interaction will give a stronger force of repulsion than this lone pair bond pair interaction. And lastly, obviously the bond pair repulsion. This will give, these two will give a stronger force of repulsion than this. I hope that makes sense. And this is what is the fundamental, like what the bonds, like the bond angles and shapes are based off of. And the bond angles that you need to know are not many, as long as you are familiar with hybridization and just understand the basic principle of the VSEPR theory. Now I'll give a table, and this table is of utmost importance. It doesn't come for many marks, but whenever it does come, you have to be able to answer it, so you need to know the values, okay? So you have to note this table down and memorize it no matter what. So on the left hand side column, I'll just have like a few examples of the molecules that follow such things, okay? And the bond pairs. So the first heading is bonds. So the number of bonds, okay? The lone pairs, the number of lone pairs, the bond angle, and shape of the molecule. So the first one is a fairly simple one. Bond pairs is either one or, sorry, bonds are either 1 or 2, and the number of lone pairs are 0. Okay, a basic example is CO2. I'll be drawing the shapes up here, okay, so, like as an example. and the bond angle is, well, CO2 is like this. So there's one or two bonds here and 0 lone pairs on the central carbon atom. So the bond angle is perfectly 180 degrees. And because it's perfectly 180 degrees or pi radians, but I'll just be giving the answer in degrees, the shape is linear. That is the shape of this molecule. Okay. Now, the second one is when there's two bonds and when there's two lone pairs. An example is water. Yeah. And let me just draw that out. So water, O, H, and H. So there's two bonds and there's two lone pairs. And recall that the lone pair bond pair repulsion is greater than bond pair repulsion, right? And therefore, this has more of a bent shape because the bond pairs here and here face a repulsion, and there's also a repulsion between these two lone pairs, and therefore the bond is like the shape is a bit bent, and therefore the angle formed is 104.5 degrees. I'll get to why this is 104.5 degrees in a bit. And the shape formed is V-shaped or non-linear. Either is acceptable. Then the very basic one, when there's three bonds and the number of lone pairs are 0. A very basic example is BF3, I think. Yeah, BF3. So BF3, it's something like this. It's like one of the carbon atoms of an ethene molecule. So 1, 2, 3. And in BF3, you see that this is a trigonal planar. It has 3 bonds, 0 lone pairs, so an sp2 hybridization, and therefore the bond angle between all of them is 120 degrees, and the shape is trigonal planar. Then another example of the same thing. No, wait, before that, let's get on to the very stable molecule when there's an sp3 hybridized atom in between. So there's 4 bonds and 0 lone pairs, and a common example is CH4, methane, and it was talked about in the previous part that the bond angle of this is 109.5 degrees, and the shape formed is tetrahedral. I have drawn the shape before, but just in case I'll draw it once again. It's something like this. H, just give me a minute. H, and then there one goes there, one inside the plane and one outside the plane. That's the shape of methane, and the bond angle between HCH is like this. These and these are all the same. It's 109.5. Now another example is it's a unique one. It's when there's 3 bond pairs and 1 lone pair, and that is the common example of that is what? Oh, this is ammonia, and the bond angle is 107 here, and over here it forms a trigonal pyramidal. No wait, pyramidal. Yeah, that's the spelling. And the shape basically is similar to the previous one when to methane. Pardon the bad drawing. Now you may be questioning as to why this is less than this when it's pretty much the same. And the reason is because, again, according to the VSEPR theory, the repulsion between a lone pair and bond pair is greater than the repulsion between a bond pair and bond pair. For CH3, it's just between bond pairs, right? So it's just between bond pairs. So the repulsion here is greater, and therefore the shape, the most stable shape, has a smaller bond angle. I hope that makes sense. Okay, and then I believe there's just 2 more left when there's 5 bond pairs, 5 bonds and 0 lone pairs. An example is, think of an example, right? PCl5. phosphorus pentachloride. And the shape formed is trigonal bipyramidal. Trigonal bipyramidal. And the bond angle is, just give me a minute, I'll show you what the bond angle is. It's something like this. So there's P, right? And it forms a trigonal planar first, right? There's a trigonal planar, and there's a Cl that's going below the P. So it's like going below P, and one's going above P. Okay, that's below and that's above. And so the bond angle between the CLs and the trigonal planar is 120 degrees, similar to trigonal planar. And the bond angle between the one that's going above or below the plane and between that and this CL is 90 degrees because they're perpendicular to each other. So this is 90 degrees, yeah. And the bond angle between the two going above and below the plane is 180 degrees. So there's multiple bond angles for this one. So, but the most common ones are 120 degrees and 90 degrees. Whichever you write is correct, but you must specify between which bonds the bond angles are between. And the last one is SF6, which is 6 bonds and 0 lone pairs, and it forms a 90 degree. And what the shape is octahedral. So as the 3D shape is something like this, one above, one below, two out of plane, two into plane. For the last two, I suggest you look up like a 3D model, like Google an image, because it's really hard to draw a 3D representation. But whenever you're asked to draw a 3D representation, you must be able to draw it like the way I drew it. And this is like a usual representation of the octahedral bond shape. And between all of them, the thing is 90 degrees, and between the one that's going above and below, it's 180. And basically between every opposite atom, it's 180 degrees. The octahedral shape is very commonly seen in transition complexes, but that's in A2. Now, the reason why these bond angles and shapes exist is because molecules like to exist, like everything in chemistry, like to exist in its most stable form. And in this shape and with this correct bond angle are the molecules most stable. For instance, if you're trying, let's say BF3, okay? If you're trying to, well, let me just draw the structure. So if you're trying to reduce the bond angle or make it into another shape, maybe something like BF3, right? If you're trying to make it something like this, eventually it will turn back to this because this is its most stable form. This is where the repulsion is least between the bond pairs, and it exists in its most stable form. I hope that makes sense. There's a video of a person that demonstrates this bond angle and shape, the reasons as to why the stability exists with balloons, like he ties balloons together. I'll try to find the video and link it below in the comment section or the description of the video, and I highly recommend that you check it out for a visual understanding of why these shapes and why these angles. That's all you have to know regarding bond angles, bond shapes, and the VSEPR theory. Now let's move on to bond polarity, the idea of electronegativity and bond polarity. So before that, let's talk about electronegativity. This is an important term that you'll come across a lot in your A-levels of chemistry. And what electronegativity basically is, like how to define it, is the likelihood or the tendency of an atom to attract the bond pair of electrons towards itself. Okay, that's what electronegativity is. This induces bond polarity, otherwise known as, or in a sense, partial charges. Okay, Now, how exactly do I, and wait, before how exactly this makes sense, let's I'll just state the trends. The trends of electronegativity is that it increases across period and up the group. And it even makes sense if you think about it, because electronegativity is like the tendency to pull it towards towards itself, right? So across the period, there is greater nuclear charge, so greater nuclear attraction. Up the group, there is lesser number of shells, so lesser shielding effect, and therefore, the stronger pull, stronger nuclear attraction of the bond pair towards itself. So it makes sense if you think about it in that way. And that's basically what electronegativity is. And how does this exactly make sense? So let's say across the period, oxygen, okay. Wait, let's just take a very simple organic molecule, methanol. CH3, assume that's H, O, and H, okay. So because O is more electronegative than H, and we don't have values, I'll just ignore this, okay. So let's just pretend that this is the only molecule for now, okay. So because O is more electronegative than H, what happens is it pulls the bond pair of electrons towards itself, like the one that holds this covalent bond together. And because of that, it gets a partial negative charge. Not fully, because it doesn't attract the electrons fully towards itself. The electrons, it's not fully, like, does not fully belong to oxygen yet. But because it has more of the bond pair of electrons, it has a partial negative charge. And this has a partial positive charge, and the way you denote that partial negative or positive charge is this. And this is basically the idea of bond polarity, is that the part, like, what an improper division between the charges, or the bond, because of the bond pair, like improper sharing of the bond pair of electrons. And this is what I mean by covalent, like a molecule never having mostly never having perfectly covalent or ionic characteristics, is because of these electronegativity values, or because of the distortion. Um, the electronegativity values, for your syllabus, you do not need to know, but what's important is that when there's a great difference, like when the difference is great, ionic bonds are formed. So let's say the electronegativity of Na is much less than that of oxygen, and therefore an ionic bond is formed. When it's substantial, polar, which basically means that polar covalent bonds are formed. An example would be OH, because it's not that much of a difference, but the difference is substantial, leading to polar covalent bonds forming. When the difference is insignificant, non-polar covalent bonds formed. And perfect examples are when diatomic molecules are formed. So like H, because their electronegativities are very similar, therefore the difference is not insignificant, and so a non-polar covalent bond is formed. And that is exactly what bond polarity is. Now, bond polarity also plays a role in intermolecular forces. So intermolecular forces, as you may be aware, are like forces of attraction that hold together molecules. So IMFs hold together molecules. And there's three types of intermolecular forces. So one is van der Waals forces, or it is known as induced dipole to induced dipole forces. Okay, induced dipole, or London's forces. There's many ways to refer to this. Either one is correct. But in the later syllabuses, in the more recent papers, this is the most used term. They don't accept van der Waals sometimes. Forces of attraction. And the reason why this arises is because, as you learned in the first lesson, electrons are constantly orbiting the nucleus in their orbitals, right? So in some time, like let's say this is hydrogen, okay, and this is another hydrogen. So the electron here, there might be an electron here, and there might be an electron here. So there's a positive charge here, like temporarily, and this is also, no wait, let's make this more appropriate. H and H. So there's an electron here, like its electron is at this point, and its electron is, this one's electron is at this point. So at this point, you see that this area, this region is more positively charged, and this region is more negatively charged. Because of this orbiting of the electrons, there's a small attraction between this positively and negatively charged area, and that is basically what van der Waals or induced dipole-dipole or London's forces of attraction is. And what influences it is the number of electrons. Oh, wait, sorry, the number of electrons. So the greater the number of electrons, the stronger the van der Waals forces. Okay, and therefore greater melting points or boiling points and so on. The second part, the second intermolecular force is permanent dipole to dipole. And this is when there's a difference between like the electronegativities. For instance, between C and O in a hydroxyl. So this oxygen has, like, it's more electronegative than carbon, and therefore it has a partial negative charge, and this one has a partial positive charge, and therefore it forms permanent dipole to dipole forces of attraction. So another the same molecule, OH, right, negative, positive, this would be attracted to this, and this would be attracted to this. Okay, and that is what the permanent dipole to dipole forces of attraction is. And lastly, the last forces of attraction is some, if you take bio, you probably know what this is. It is hydrogen bonding. And hydrogen bonding is formed when a hydrogen is directly attached, like a polar bond is formed between a hydrogen and a very electronegative atom. So, and more specifically speaking, it's when F, O, or N. So when either of these three molecules, either of these three atoms are attached to a hydrogen directly, it forms hydrogen bonds. So a very basic example is HF. So when there's HF, this has a partial negative charge, this has a partial positive charge. So another HF, and this is partial negative, partial positive. Hydrogen bonds are formed between the hydrogen, the partially positively charged hydrogen atom, and a lone pair of an adjacent fluorine. So something like this. That's how a hydrogen bond is denoted. Another example, a very common example again, is water. This is positive, right? And there's another oxygen, H and H, right? I won't draw the partial positives here. And this is partially positive, so it's attracted to this, and this is attracted to this, right? And so on. This is how water molecules have cohesive forces. This is why they're liquid at room temperature, despite them supposed to like be a gas. Despite them supposed, what? Sorry, incorrect English. But yeah, they're supposed to be a gas at room temperature and pressure, but they're not, and that is because they have extensive hydrogen bonding between each molecule. Now, you know the three types of intermolecular forces. Now let's think about their strengths. Which do you think is stronger? Now, you don't need to know the reason why, but this is how the order of strength goes. H bonds are stronger than permanent dipole to permanent dipole forces of attraction, which are stronger than induced dipole to induced dipole forces of attraction. And this is how it goes. That's all there is to it. You don't really need to know much more about this. Yeah, there isn't much to know about this. But you must know that whenever there's edge bonds, it's stronger than the rest, and therefore it's more likely to have the molecules with edge bonds are more likely to have a higher melting point or boiling point. One other thing that the induced dipole to dipole forces of attraction are influenced by is something that I just recalled because it comes in organic chemistry many times, is induced dipole to dipole. So you know that one is number of electrons. Okay. The second thing is the contact, the area of contact point. What I mean is, So let's say there is CH3, CH2, CH3. No, it's CH2, CH3, right? And CH3, that's one, CH, CH3, CH3. Now, which do you think would have a higher melting or boiling point? Now, I'll give you some time to think. Okay, so if your answer was this, then you're right. And the reason, sorry, if your answer was this, then you're right. And the reason is because uh, they're both the same molecule. They're like isomers of each other, and therefore the number of electrons are the same. So it's not due to a difference in number of electrons. Whereas this is an unbranched molecule, and therefore it has like a larger area of contact point. Whereas this is a branched molecule, so the contact point is lesser, and therefore this has a stronger induced dipole to dipole forces of attraction, and therefore higher melting point. And those are two things that induced dipole to dipole forces of attraction like depend on, like the strength. Okay. And lastly, there's two more things that I needed to talk about, and one of them being like the changes of state. Okay. So in changes of state for ionic lattices or ionic compounds, to change, for example, NaCl, to change it from solid to liquid, you have to break or weaken the ionic bonds. Okay, I hope that makes sense. And the same for metals. You have to break the metallic bonds. But for covalent, there is a slight exception. So for covalent, there's two sections. For simple molecular structures, you have to break or weaken the IMFs. Okay, so for example, Cl2 or what's another example of basically diatomic molecules and other things. But for giant covalent, you have to break the covalent bonds to cause the change in state. So for example, SiO2 or Si or diamond. So the reason this has a higher melting point, a much higher melting point, is because you have to break the extensive covalent network within the molecule to cause a change in shape. Whereas for this, you have to break just the IMFs or weaken the IMFs, and the IMFs are much weaker than uh, the covalent bonds. Okay, like for instance, a covalent bond might have like 300 to 400 kilojoules of energy to require 300 to 400 kilojoules of energy to break. Whereas like the strongest intermolecular force, which is the hydrogen bond, I believe, yeah, which is the hydrogen bond, takes about 40 to 50. Whereas induced dipole to dipole takes around 1 to 10, if I recall correctly. So this is why giant covalent molecules have a much higher melting point. That is something you have to remember. And let's transition into one last thing, which is the trend of melting points down group 17, or better known as group 7 if you're not used to including the transition elements in the periodic table. So it's F, Cl, Br, I, and then astatine. Now remember the symbol for astatine. We don't normally consider F because it's an anomaly. So when we say group 17, we normally just consider these three, Cl, Br, I. And what would you think is the trend of melting points down this group? The answer is that down group 17, the melting point increases. And that is because the number of electrons increases, and therefore the strength of induced dipole to dipole forces increases. Or you can just sometimes you can say it in the broad spectrum, which is the strength of IMFs increases, and therefore more energy is required to break the IMFs. That's one trend. However, when you think about the what hydrogen halides, so HF, HCl, HBr, and HI. What do you think would be the case for this down the group? Well, if you're thinking about HCl to HBr and HI, the answer is the same. Down the group, the melting point increases because increasing number of electrons. However, HF is an exception, and that is because F is highly electronegative, and therefore HF molecules form hydrogen bonds with each other, and hydrogen bonds is the strongest IMF. And therefore, the trend in melting point goes something like this. What with temperature? Yeah. So it goes something like this. This is for HF, this is for HCl, and this is for HBr, and this is for HI. That's how it goes. This is an anomaly because it has hydrogen bonds. I hope that makes sense. And that is all for the lesson, chemical bonding. If you do have any doubts, please leave them in the comment section below.